Hello physicists, we're going to talk about the Doppler effect today, and there's a great YouTube video that I put in the comments for this one that you should watch before you do the Doppler effect lab with me. Basically, the Doppler effect is the idea that sound waves are compressed relative to the observer if an object that is making a sound is coming towards you, and the sound waves spread out if you are behind the object, if it's heading away from you. So if you've heard a fire engine go vroom, or cars on the freeway make a noise like that, it's because the pitch of the sound that the car is making is changing relative to you. It's not changing if you're in the car, because you don't hear a noise like that if you're in the car, but as the car goes by you, it's changing relative to you. Here's another picture that gives you a bit of an idea. If this is an object that's making a sound, the wavelength is getting shorter ahead of the object that's traveling in this direction, and behind the object the sound waves are stretching out and you're hearing a lower sound. Here's an example of the Doppler effect from a swan. You can see ahead of the swan that the water waves are being compressed. It's not always sound waves that we're talking about here. Ahead of the swan they're being compressed, and behind the swan you can see the ripples kind of spreading out a bit. So let's head to the virtual lab. This is a little bit of what it looks like, and figure out some more things where we can actually measure the hertz of the sound as the car is coming towards us and moving away. Just in case you forgot where the virtual lab is, you can go to the lesson 7.09, click on it, and then down here in the right hand corner go to the fourth screen out of 5, and click right here where it says Virtual Lab. Before you start, make sure you click the green button right here to start the to deploy the microphone here. They send a technician out in a truck and drop off the microphone. And then you can put in the speed right here. You want the car to go, and the car is making a noise of a constant pitch. And then you can start the car. And we'll watch the oscilloscope to see what's going on, how the frequency changes. So let's do that again, and watch the hertz here. Watch how the hertz, what happens to this number here as the car goes by. You can see it's 88, then it goes down as the car goes by. It goes up as the car comes towards us, and it goes down as the car goes by. So let's just take a second looking at this. The black line here is before the microphone, and the white line here is after the microphone. So you can see that there are different wavelengths here. So here's the lab sheet that we're working on. Make sure you download it from Doc Sharing. And here's the big idea. Sound waves move with a moving object, whether the moving object is the sound source or the observer is the sound source. You're going to find out in this lab, you're going to produce a Doppler effect and see how the pitch changes. The pitch is the frequency of the sound wave. It's what you hear in terms of frequency. The microphone, the graph was created by a microphone picking up the sound of a car coming toward the microphone and then continuing to drive past. What was the car's speed? Here's the car's speed right here. And what does the white line and the black line show? Well, they have a key right here. The black line is before the microphone, and the white line is after the microphone. You can see there's a difference in wavelength and a difference in frequency. The frequency of the black line is about 100 Hertz, and the frequency of the white line is about 60 Hertz. Which line has more waves per second, and how do you know? Well, we know that hertz means cycles per second, or wavelengths that go by every second. So if more waves are going, if this has a higher hertz, more waves are going by every second on the black line. And remember, the black line is before the microphone. Those waves are getting kind of pushed closer together relative to the observer. And you probably know the question to answer the answer to question 5 just from your personal experience. If you've ever heard a fire engine or an ambulance or cars on the freeway goes by, you kind of go, eeeem. They start higher and they go lower. That's because the frequency here is higher when those sound waves are getting compressed, pushed together. Remember the picture of the swan where you saw the waves kind of smooshed together? There's a higher frequency, so you hear a higher pitch. Pitch is just the sound, the frequency of sound waves. It's how we describe what sound waves of different frequencies sound like. So if we hear high frequency waves, we say that's a high pitch. If we hear low frequency sound waves, we call it a low pitch. So you should have answers to all the questions that are in your lab sheet, but I am giving you a little Easter egg bonus question here. You can type this into the bottom of your lab sheet for an extra point or two. What is infrasound? And I'll give you a hint here. Generally, I don't recommend using Wikipedia, but here's a great little paragraph on infrasound, and you can learn all about it. It's especially interesting if you scroll down here and you look at animal reactions to infrasound. The earthquakes and tsunamis, the animals often hear what's going on before the people detect what's going on, and the animals, because they can hear at a lower frequency that we can, they're very good at warning us about things that we don't know are happening yet because we don't hear them. Dogs can also hear very high-pitched sounds, and you can also write me a few sentences about that if you would like. Thanks so much for coming to lab. We'll see you next week.